Hello, my name is Colin Agor, and this is my REU presentation on the WIPAR design tool analysis for use in developing hypersonic Waveriders. This software was developed by Dr. Kenneth Senner in the early 1990s to more accurately and interactively develop hypersonic Waveriders for the aerospace engineering field. Originally, this program utilized the Silicon Graphics Octane series, which used the IRIX operating system. We were tasked with utilizing a standalone and creating a standalone version for Python or a similar program that can be used with Windows 10 so that this really great tool can be used in modern times. This program has been used on many AFRL and NASA studies to help them design fantastic vehicles and to verify that the data they're getting from outputs are verified in the real world and can be consistently found in actual test flights. What we wanted to do was to compile a detailed knowledge base of WIPAR's publications, interface WIPAR's process through Python so that we can use it with current systems, and maintain as many current program features as we could. This was pretty challenging, especially because with the lack of the GUI, we didn't have all of the interactive portion, but it is still really easy to iterate using Notepad++ and just recompiling the Fortran code through a Python code base and running that in Ubuntu terminal to actually get our output graphs that are all saved in a local folder, and it's nice and easy to access. We also wanted to do a comparison of how this stacks up to other similar programs in the field, things like ANSYS or SimWorks, and we've actually found that this is kind of one of a kind. There's not many programs that are custom built just for Waveriders and for hypersonic technology. ANSYS does do simulations that are in that field, but they take a long time, and this is pretty much instant. It takes at the max a few minutes to make all of the design changes you want, recompile it, and run the actual solver to get your output graphs. So it's a lot easier than having to go through and find all of the different parameters, build your model in something like SolidWorks, import it, and then run that simulation. So with our results, we've actually been able to verify the output plots for the Mach 6 Langley vehicle over what was published in an actual paper that was originally from the author and was verified by NASA, AFRL, and some of the different universities around the country. You can see it's kind of obscured by my face right now, but to the left of my little icon there, you can see a set of 4 plots. The top 2 are our output plots by themselves, and the bottom 2 are overlaid with their axes adjusted to be to scale with the plots that were in that actual document. So you can see they match up perfectly, and we're really happy with how this is looking. For the future, we're going to continue the verification of this with other vehicles to make sure that all of this works, because currently we only have inviscid calculations, so we're going to work on getting the viscous ones up and running. But we've ironed out all of the errors that were occurring early on in the project and have actually really fantastic output plots that are confirmed to be correct. So we're very excited to see where this is heading. And overall, just really excited with how this research is going to be affecting our time in different contracts and actually be able to be applied with current things that AVD Lab is doing. But yes, I look forward to seeing how this is applied in the future.